All right, so this question is going to be a little bit more like what you might see on an AP exam. All right, we do have a couple of different temperatures over here. We have a metal rod that's connecting from the 100 degrees down to the 0 degrees Celsius, slightly different lengths, different materials, which means they're going to have different heat transfer coefficients here. I've got the transfer coefficient for steel, which is 14 joules per second meter Celsius, and then the copper, which is 390. All right, now one of the big ideas that's going to be important as we start to work these problems is recognize that if I have one continuous rod, even if it's different materials here, going from one side to the other, delta Q over T is going to be a constant. It's going to be the same all the way through. Now that should kind of make sense, because if for some reason I start getting heat to transfer more quickly in one of the metals than the other, then what's going to end up happening is that the temperature here is going to build up and it's going to get higher. And if this temperature is higher, then what's going to happen is that means the heat's going to transfer faster now through the second one. And so it's going to balance out. No matter what, your heat transfer coefficient for a single path is always, sorry, not the coefficient, but the heat transfer rate is always going to be constant for a single path as it goes through, even if those are different metals. Now, with that, we're going to go ahead and use the equation that we learned in the previous video, that Q over delta T. Sometimes they put a delta in front of the Q, but in our formula packet, it's just Q over delta T, because Q is the amount of heat being transferred, the change in energy, the amount of energy that's being moved through. That's going to equal K A delta T all over the length. So what we're going to do is we're going to separate the steel and the copper. So we're going to look at the steel first. We're going to find the heat, Q over delta T, for the steel, which is going to be 14 times the area. Now, if you haven't had a chance to read through the question, now would be a great time to do it. It does say it has a square cross-sectional area of 2 centimeters on a side. So that means I'm going to need to do 0.02 squared, and that's going to give me the area then of this cross-sectional area, which was 2 centimeters on each side, and then times the delta T. Now, for the steel, it's going to start at 100, and then this is the temperature at the junction. And so that's going to be my T there. So it's 100 minus T. And so we hopefully will be able to solve for that T there. All right, and then we're going to divide by the length, which is going to be 10 centimeters, which is 0.10. And so that way we'll end up getting a positive heat transfer moving to the right. Now, at the same time, we actually have two variables here, right? You have the heat transfer rate, and you have the temperature at that T. So it would be nice if we have another equation. So let's do the same thing now for copper. So we're going to go Q over delta T. The heat transfer coefficient for copper is 390. Then we have the area, which is still going to be that 0.02 squared. Now here, my starting temperature is going to be T, and the ending temperature is going to be 0. So I'm going to go T minus 0 there, and then divided by the length of that one, which is going to be 0.20, because it's 20 centimeters. Now, at this point, I can say, well, because it's all one path, those two rates of heat transfer or heat flow have to be the same. These guys right here need to be equal. And so what I'm going to do is just put them together. So I'm going to say that means that 14 times 0.02 squared times 100 minus T over 0.1 must be equal to 390 times 0.02 squared times T minus 0 over 0.20. And those two things are going to have to be equal. So now let's go in and do some math. I'm going to divide both sides by that 0.02 squared, so that's actually going to cancel out. I'm going to go ahead and divide 14 by 0.10, which is going to give me 140, which then will be times 100 minus T. And then on this side, I'm going to divide the 390 by the 0.2, and that's going to give 1950 times T minus 0. And now I should be able to just kind of do my distribution and hopefully solve for T. So I'm going to end up with 14000 minus 140T is equal to 1950T, and then minus, when I take that over, that'll be 0. So I'm going to add the 140 to the other side, plus 140, and that will give me 14,000 equals 1950 plus 140 would be 2090T, and then we just divide both sides by 2090. So 14,000 divided by 2090, and I get 6.69. So I'm going to go 6.7 degrees Celsius equals T. All right? Now, I know what you're thinking. You're thinking, well, isn't that really low? Am I really going from 100 down to 6.7 degrees there, and then from 6.7 down to 0? That seems like that's a really low number. Well, remember that this is based off of those heat transfer coefficients. When you look at the heat transfer coefficient of copper, it's really, really high. That means if you had a really high temperature here, then it would have a really, really high flow rate here. Because the flow rates have to be equal, having a low temperature here means that with the higher heat transfer coefficient, we're going to end up having a very similar, actually equal heat flow rate. So 6.7 degrees Celsius actually makes a lot of sense to have a very small number there to be able to balance out those heat transfer coefficients. Now, the other question here is find the temperature at the junction of the two bars and the total rate of heat flow. So in order to find the total rate of heat flow, we're just going to take that temperature, put it into either one of these two equations. It shouldn't matter because they're equal, right? I'm going to let you go ahead and do that because you don't need to watch me do algebra and punch numbers into my calculator. You should hopefully get 5.2 watts or joules per second. All right, so give that a try, and once you got it, move on to the next question. So I'm ready to move on to the next question. This one's a little bit different because now the copper and the steel, same bars, right? That 20 centimeter copper and the 10 centimeter steel, now those are connected from one side to the other kind of by themselves, right? Now, if you think about it, the last one was kind of like a circuit in series. If you've ever looked at circuits before, a circuit in series, all of the current has to go through a single wire. And so the current is the same for all those wires, which is literally what we did on that previous slide. Now on this one, the current does not have to be the same, right? I can have some going through the copper and some going through the steel, and because they're not connected, the amount of current going through those can be completely different. So the heat current or the heat rate of heat transfer can be very different between those two. In fact, the one that has less, shall we call it, resistance is going to have a much higher heat flow rate, right? So if you'll remember, I had the heat transfer coefficients on the previous slide. So let me go ahead and write those here. So now we should be in a good position to answer the question of the total rate of heat flow in the two bars. So we're going to find them individually. So we're going to do the copper first. We're going to do Q over delta T. That is going to be equal to, remember our equation is K. So we're going to do the copper, that's up top first. So I'm going to do the copper, the K is 390, times the cross-sectional area, which it's still that 2 centimeter square. So 0.02 squared. All right, and then times the delta T, which here is going to be 100 minus 0, because it starts at 100, goes down to 0. And then we will end up dividing by the length, which was 0.20. And from there, we should be able to calculate the heat transfer coefficient. I'm going to go ahead and write down the formula for the steel one, and then we'll go ahead and punch both of those into our calculator at the same time. So Q over delta T, now I'm doing the steel. So the steel has a K value of 14. then 0.02 squared, 100 minus 0, because it's the same hot and cold there, and then divide by the length, which was 0.10. So now I'm ready to punch both those in. So let's go beep, 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 beep. And we get 78 watts for the copper and only 5.6 watts for the steel. Again, that makes sense. The copper, even though it's longer, it definitely has a much larger heat transfer coefficient, so it's going to be able to move that heat from one side to the other very quickly. Now, the question is the total rate, so we'll go ahead and add those together, and that will give us our final answer of 83.6 watts. And there you go. Hopefully that was helpful in looking at a couple of different examples of heat transfer. For tonight, for homework, you'll get to try several more of these in different ways. All right, so have a look. Please do let me know if you have any questions, and I'll see you next time.